Okay, so I know I ended that first lesson very abruptly, but I was right down to the very last second. So we're going to finish up pretty quickly. So we were talking about this series, and we said they were bigger than convergent, and I left that on means question mark, right? If I fit through the door, will Kevin Durant fit? The question is, who knows? Like I said before, it could be a perfectly me-sized door, and if I fit, Kevin Durant can't fit. Or it could be a door the size of the arch in the front of the building, and then, yeah, we both can fit through that door. So I don't know. So I need a backup test. And the backup test is called a limit comparison test as opposed to a direct comparison test. The limit comparison test says this, okay? If the sum of the a sub n's and the sum of the b sub n's are both series with positive terms, if the limit as n approaches infinity of a sub n divided by b sub n equals c, where c is a finite number greater than 0, positive finite number, then either both series converge or both series diverge, okay? The reason for that is if you look at this limit, okay, what this is essentially saying is that, okay, so I rewrote our original limit, and what I did was I broke up the limit of the quotient to be the quotient of the limits. So essentially limit as n approaches infinity of a sub n divided by the limit as n approaches infinity of b sub n, and then I multiplied both sides by the denominator, and I ended up with this. The limit as n approaches infinity of a sub n is equal to c times the limit as n approaches infinity of b sub n. I want you guys to think about the implications of this statement. So pause the video and think about what this is essentially saying is the relationship between the sum of the a sub n's and the sum of the b sub n's, and then you can come back to me. Okay, and I'm hoping that some of you guys realize that what this means is that my a sub n's are essentially a constant times the b sub n's. And one of our rules when we were first talking about series is that if the sum of the a sub n's, well, here I'll say the sum of the b sub n's converges, I can multiply that series by a constant, okay, and I could either do it outside the summation or inside the summation, and that new series will also converge, okay? Or, conversely, if the b sub n's is divergent, and I multiply that series by a constant, that new series will also diverge. Okay, so essentially that's what the limit comparison test is doing for us. So I want to go back to example 4, where a direct comparison test failed us, and I want to try a limit comparison test this time. So I'm still going to start the test the same way. So I'm going to start it over here by saying what I'm comparing it to. I'm still going to compare to key term over key term. I'm still going to state how I know this series is either convergent or divergent, and which one it is, if it's geometric or p series. But instead of having to do this step, I'm going to go straight to taking my limit as n approaches infinity of the ratio of this series to this series. So try to set up your limit, pause, and come back. So I'd have the limit as n approaches infinity of n plus 1 over n times 4. Oh, sorry, wrong one. Sorry about that. So I want the limit as n approaches infinity of 1 over 2 to the n minus 1 divided by 1 over 2 to the n. Okay. Simplify it, finish up your limit, come back to me. Okay, rewrite this way. Fraction, instead of divide by a fraction, multiply by the reciprocal. Okay, and then instead of L'Hopitalling this or anything, because I am going to get infinity over infinity, I will do an end behavior model, which will give me a similar limit of 2 to the n over 2 to the n, which is 1. Okay, I am getting a positive real finite number here, which means that both series do the same thing. Okay, so because this one is convergent, this one is also going to be convergent. Okay, let's look at another example, just one last one. I want to know if this series is convergent or divergent, the sum of n plus 1 over n times 4 to the n. Okay, and what I'll do to kind of safeguard myself, I'm going to go through, it's not a geometric series, it's not a p series, nth term test because of that exponential in the denominator. Okay, and after ruling out geometric and p-series and nth term test, I'm going to not necessarily specify which comparison test is I'm going to go with, but I'm going to try a comparison test. So right now I'm just going to state that I'm going to compare this to the key term over the key term, the sum of the key term over the key term. So go ahead and figure out what that key term over the key term should be. And this one's a little tricky, and you got to be careful because we have a product in the denominator, not a sum. Okay, usually when we look at key terms, if I had n plus 4 to the n, one of these would dominate, but because it's a product, that's a single term there. So I'm just going to say that I'm going to compare two. Okay, and the key term over the key term, you should come up with. Okay, this would be my key term over the key term. The key term from the numerator is n, okay, and I can separate that from the plus 1 because they're being added, but because of the product in the denominator, that is one single term, n times 4 to the n. If I simplify this, I realize that this is really the sum of 1 over 4 to the n, right, because now that I just have an n in my numerator, my n's can divide out, and that is really the sum of 1/4 to the n, which is, well, pause and think about that, convergent or divergent, geometric or p-series. Okay, and you should have decided that that was a convergent geometric series with the absolute value of r equal to 1/4, which is less than 1. Okay, my gut instinct is always to, once I show what I'm comparing it to and whether or not that series is convergent or divergent and how I know, my gut is always to try a direct comparison test. So the first question I'm going to ask is, what is the relationship between the two terms? So consider what the relationship is between these two terms, okay, and decide, pause, and come back to me. See if the test works or if the test doesn't work. Okay, so I want to know what the relationship is here. Okay, and again, here's the advantage to comparing it to the original form. Okay, when I compare it to the original form, I usually have something in common. So here my denominators are the same, but my numerator is bigger. And if the numerator is bigger, that means that the quotient is larger. Okay, and if the quotient is larger, that means bigger than convergent. That's just like the last situation. Bigger than convergent means the test fails. Okay, and when that test fails, I'll move on to a limit comparison test. So try to use the limit comparison test. Set up your limit of the series you're looking at versus the series you want to compare it to. We don't need absolute values here. The main reason for that is that we've just said that our series have to have positive terms in it. So a limit with no absolute value. Set up your limit. Pause and come back to me, please. And here's that limit that accidentally snuck in a little earlier than it should have. Okay, so I have the limit of the term of the series that I'm looking at, n plus 1 over n times 4 to the n, divided by the term that I know about, which is n over n times 4 to the n. Okay, so go ahead and finish this up, simplify it, and come back to me. Okay, so first I'm going to get rid of the quotient divided by quotient, and then I'm going to do an n behavior model on this. Well, I can simplify a little bit. That doesn't look right. Hang on. That's much better. Okay, so now I've actually multiplied by the reciprocal, and now I can have terms that divide out. Okay, terms that divide out, and I see that this is the limit n approaches infinity of n plus 1 over n, which I can either L'Hopital or n behavior model, and I should get a value of 1. Okay, if you look at the wording on limit comparison test, if I get a positive real finite number, then both series agree. So whatever my first series is doing, whether it's converging or diverging, this series is going to do the same thing. Okay, so this one was convergent, which means my new series will also converge. Okay, had the original series diverged and I got a positive real finite number, then this series would do the same thing. This one would also diverge. Okay, and that is all.